So you just saw a remarkable demonstration from Johann Roca in which he cooked a dish using this very strange device called a rotovap. So I now want to explain to you how a rotovap works. And indeed, as you will see, the principles of operation of a rotovap are absolutely explained by the physical principles that we've talked about this week. So to explain this to you, let me first ask you to imagine the following problem. So imagine that you take your favorite drink. It may be Coca-Cola, it may be orange juice, it may be a nice glass of wine, and you know that when you drink your wine or your Coca-Cola, there's some flavor molecules within it, which are what really makes you happy when you drink it. So imagine that you decided that you would be much happier if you could only if you could have a liquid which doesn't have all this other stuff in it, not all this water. It only had the flavor molecules. That is, it was really a very, very concentrated mixture of only the flavor that you like to drink. Then that is essentially what Johann was trying to accomplish, and indeed did accomplish with the rotovap. And what I now want to do is to explain to you how you would do this. So let's first by remembering the equation from this week. So the equation from this week was that U interaction is equal to C times KBT. And what that represented, remember, is the physical balance between the fact that on one hand the molecules like to stick to each other, that's the interaction energy, and on the other hand they like to jiggle around, which is the KBT. And when these two are equal, that's when the molecules start to evaporate off, that liquid becomes a gas. But now what I want you to imagine is that you have a liquid which is contained of many different materials. So just for the sake of argument, let's imagine that you have a cup and it's filled with red molecules and blue molecules. And imagine that the red molecules stick to the red molecules and they also stick to the blue molecules. And the blue molecules stick to each other and they also stick to the red molecules, but they stick with different strengths. So maybe the red molecules are very weak. That is, they bond to each other and to the blue molecules very weakly, whereas the blue molecules bond more strongly. So the question that I want you to imagine is, how can we separate the red molecules from the blue molecules using only the principle of the equation that we've told you about? So let's think about this. So for the red molecules, given that they have some interaction energy, there's some temperature at which the red molecules will boil if you have a substance of pure red molecules. Similarly, if you take the blue molecules and you put them together, there's some temperature at which the blue molecules will boil. It's the interaction energy of the blue molecules divided by CKB. So what you might imagine is that if you were sitting in a temperature that's somewhere between the temperature for the red molecules to boil off and the blue molecules to boil off, what you're going to get is mainly red molecules boiling off. You're not going to get only red molecules, of course, because the red molecules and the blue molecules stick to each other as well. And so it's going to be a little bit more complicated than that. But if you imagine now our liquid, which has red molecules and blue molecules, has a vapor on top. And in the vapor, there are more red molecules than blue molecules. So now, of course, the vapor is a gas, and you can't drink a gas. But if somehow we could capture that gas by sucking it out or whatever, and then making it back into a liquid, we would have formed a substance which has more red molecules than blue molecules, and you will have therefore concentrated the material. And this is basically the physical principle that's at work when Johann is using the rotovap. It also is, as I will explain in a little while, the physical principle which is at work when you decide to distill whiskey or alcohol of any sort. And it's essentially the way that one separates, one component of a liquid from another. So now let's go back to the rotovap. Let's imagine that you were a famous chef like Johann Roca, and you wanted to distill the essence of eucalyptus or dirt or chocolate or something to serve in your restaurant to the diners. So you really want your diners to have the full experience of the material that you're giving them. You don't want it to be contaminated in any way. So let's think about the way that I just described doing it. So what I said is you should take your dirt, if that's indeed what you're going to serve in your restaurant, and you are going to heat it up. And then you're going to basically collect the more volatile compounds within the dirt, and you're going to serve that to your diners. Now, the one problem with that, besides the fact, of course, that it may not be wise for a restaurant to serve dirt to their diners, is that when you heat up the material, there will be chemical reactions between the volatile components, and you will change the flavor to some extent above, to make it different than what it was. And if you're really trying to preserve the essence of the material, you don't want to heat because you know that heat will change the flavor. So somehow we have to figure out a way to cause this phase change without heating. So how can we do that? So the answer to that actually is sort of sitting right in front of you if you remember the phase diagrams that we've talked about thus far this week. So here again is the phase diagram of water. And remember that we said that water can become a gas, liquid water can become a gas by increasing the temperature from 23 degrees to 100 degrees Celsius if you're sitting at 1 atmosphere of pressure. But you also can change the phase of the water by changing the pressure. And keeping the temperature fixed. So if you look at the phase diagram of water, if we're sitting here at 23 degrees Celsius and we drop the pressure sufficiently, at that point the water, while maintaining the same temperature, at that point the water will become a gas and it will actually vaporize. So the pressure at which a material vaporizes at a given temperature is what scientists call the vapor pressure of a material. And the concept of vapor pressure both suggests a solution to our little conundrum. So this is what I want you to now do. So let's take the phase diagram that we had, with these three different phases, and I want to get rid of all of it except for the phase boundary that corresponds to the liquid-gas equilibrium boundary. And so this plots the pressure as a function of temperature. So this curve, which basically represents at every temperature the pressure at which the gas and liquid are in equilibrium, is called the vapor pressure curve of a material. We can put the curve down for water, and we can also add different substances on top of it. We could add alcohol, for example, or we could add a flavor molecule. And what you see is that these curves, which happen at different positions for the different materials. So, for example, alcohol, which consists of ethanol, which consists of molecules that are bound more weakly to each other than water, has a different vapor pressure than that of water, and so on and so forth for the vapor molecules. So now let's imagine that we could do the following experiment. Instead of increasing the temperature to cause the more volatile compounds to come off, what we're going to do is instead decrease the pressure. So we're going to sit at the same temperature and decrease the pressure. What you see from our curves is there is a critical pressure where the most volatile compounds will start to come off much more than the others. And so the gas that's above our substance will be rich in the more volatile compounds, only by changing the pressure, not by changing the temperature at all. And as you decrease the pressure further, more and more of the different compounds will come off. But if you do this carefully and you somehow are able to collect the volatile compounds, the gas off of, that you have and sort of reconvert it into a liquid, then that will allow you to separate the two different compounds. So with that in mind, let's go back to the Rotovap, to this big clunkety-looking machine that Johann Roca was showing you, and let's talk about the different pieces and about how they work. So the Rotovap consists of really two main parts. I guess you could argue there are more than two main parts, but for the purposes of the discussion here, let's just say there are two main parts. There's this big bowl at the bottom, and this bowl is where you put the thing that you would like to vaporize. So you can put in your eucalyptus leaves, you can put in your chocolate, you can put in your Coca-Cola, whatever it is that makes you happy. If you go and you're fortunate enough to have a Rotovap in your kitchen, you can choose what you put into this thing. You then attach it to the thing, and then there's a vacuum pump or some sort of pump to lower the pressure in this big container, and you simply lower it enough so that the most volatile components start to come off. So, and at that point, of course, you have a gas which is rich in the volatile components and much less rich in the non-volatile components. And then remember, we have to take that and convert it to a liquid or something that we can carry away. So this is done with the condenser coil. So at the top there are these condenser coils which essentially cool, essentially make the temperature in that region much cooler than they are in the rest of it. And if you then cool, you will then actually cause this gas to recondense into a liquid, which is captured at the bottom in the second flask. So oftentimes at the position of the second flask, people put like ice around it or something to keep it cool, to make sure that it doesn't revolatilize. And if you just continually run this thing, you'll end up with a liquid jar like the one that Johann told you, which is strongly enhanced for the flavor molecules that you want. So that is how a Rotovap works. That is the principle through which it works, and that's what Johann was using. Now, before we leave this discussion, I want to just mention one other important process in cooking that is related to this that we will come back to later on in this course, which is the general process of distillation. So in several weeks in this course, we will discuss fermentation, which is the reaction that microbes used to basically convert sugar into ethanol. That's the sort of principal reaction in which ethanol is created when making wine, for example. So it turns out that the alcohol content in wine is somewhere between 10 and 20% ethanol. That number, as we will explain to you when we get to this part of our course, comes from the sugar content that's in grapes. I mean, unless you sort of dump extra sugar in or something, then you're sort of stuck with that percentage. But you all know, for those of you who like to drink hard liquor, or even those of you who don't like to drink hard liquor, you all know that the ethanol content actually gets well above that of that in wine. And the question is, well, how would you enhance the ethanol content? So the answer is right in front of us. It's the process that people call distillation, in which one simply uses the fact that ethanol molecules are more volatile than that of water, and thus by decreasing the pressure or increasing the temperature, one can actually create a gas which is strongly enhanced in the ethanol content over the water content. Distillers have a cool part too, where you recondense the gas into a liquid, and you then have a liquid which has a higher concentration of ethanol instead of water. Now, if you're interested in very strong ethanol contents, or for that matter, if you're interested in very strong flavors from your Rotovap, one thing you can do is to notice that in the condensate that you get out of either the distiller or the Rotovap, it's not going to be pure substance. That it's not, in the wine example, you're not going to have pure ethanol. In the eucalyptus leaf example, you're not going to have pure flavor of eucalyptus. There's also going to be water and other compounds within it, because in the gas above the liquid, there's always other molecules other than the ones that you want, that you're trying to collect. It's just that, the principle that we're using is that it's strongly enhanced in the molecules that you're trying to collect. But what you can do is sort of put it back into the Rotovap or put it back into the distiller and do the process again and again. And if you do that, then you will actually increase the concentration further of either the flavor molecule, if that's what you want, or the ethanol, if that's what you're trying to do. There is a limit. If you all go to the liquor store and watch, you will notice that even pure ethanol, that is, even the purest grade ethanol is not actually 100% ethanol. It's something like 96%. And that's because of the peculiar properties of ethanol and water, which make it really very, very hard to get that last couple of percent of water out. But anyway, in summary, what I hope you now see is that this principle that we've been talking about of the balancing between sticking and jiggling is really at the heart of the process of both rotovaps and distillations, and hopefully this explains a bit more about how Johan's remarkable creations work.